In section 3.3, we're going to talk about the rate law. Now, the rate law allows us to look at the rate of the reaction and determine the impact any reactant's concentration has on the rate. Okay? So the rate law is different than the rate expression. The rate law expresses the relationship of the rate of a reaction to the rate constant and the concentrations of the reactants raised to some power. So let's take a look at what that means. So let's say I have a reaction. Again, it's A plus B gives me C plus D in the lowercase letters that indicate the coefficients in the balanced equation. The rate law here would be, the rate law is the rate times some constant times the concentration of the reactant A raised to some power x. Now this power x is not the same as the coefficient in the balanced equation, times the concentration of B raised to some other value we'll call y, which is not the coefficient in the balanced equation. And here we are looking at the rate is only dependent on the concentrations of the reactants and it's not the products. So let's take a look at how we would use this. Now, one of the most important things to recognize about kinetics, again, is this is an empirical science, and the rate information comes from running experiments and collecting data about what happens to the reactants during that reaction. Okay, so here I have a reaction of A plus B going to C plus D. And I've created a plot. So we've run this experiment multiple times using different concentrations of A, right? X-axis is concentration of A. So starting with different concentrations of A, and we looked at what impact does that have on the rate of the reaction. Okay? So let's take a look at what we can tell from this line. So first of all, we notice that we have a straight line relationship. So what we can say is that the rate, which is the y-axis, is directly proportional to the concentration of A, which is the x-axis. We could also say that rate is equal to some constant times the concentration of A. You know, this is a straight line with no y-intercept, and think about it, y equals mx plus b. There's no y-intercept here, it's right at 0. So the rate, y, so we could call this the rate, is equal to the slope, which in this case is k, times the concentration of A. Okay. So k is called the rate constant, and k has units and is obtained by solving the equation for k. So we'll look at how we do that. Okay, so let's take a look at what we've said so far. So first of all, when we're talking about a rate constant, it is a lowercase k. It's not a capital K. We'll use capital K's elsewhere in the course later. And it always has some units, and we obtain those units by solving for k. So if this is the expression, we can solve for k by saying it is equal to the rate divided by the concentration of A. So if I know the rate of a reaction and I know the concentration of A, I can solve for K. And if I know the rate, every time the reaction is run, as long as it is at constant temperature, I will get the same value for K. It's important to note that it's at constant temperature. If I change the temperature, my K will change. But at the same temperature, it doesn't matter whether I start with concentration of A is 0.1 molar or 0.5 molar or 0.9 molar, I'm going to have the same K. Okay, so let's take a look at this balanced equation. Okay, and let's say we have run some experiments and determined the rate law based on those experiments, which was determined to be the rate constant times the concentration of NO raised to the 2 power times the concentration of H2 raised to the 1 power, right? Now, even though this 2 and this 2 are both 2's, it is not an automatic thing. This doesn't, it is not, whoops, it is not the coefficient, okay? In this case, they happen to be the same thing, but if you look at H2, its power is 1. Okay, so for some terminology, we say the reaction is said to be second order in NO. So the second comes from this exponent, or we say second order with respect to NO. We'd say that the reaction is first order, and that first order comes from the exponent in H2, or the reaction is first order with respect to H2. And then if we add all of the exponents in the rate expression, we get the overall order. So in this case, it would be 2 plus 1, or third order overall. Now, orders can be 0, and that does happen. We'll see it in some examples. And that occurs when the concentration has no effect on the rate. Doesn't matter how much I put in, it doesn't change the rate. Orders can also be fractions, and in fact they can even be negative. So let's take a look at this problem. Let's look at what this rate law tells us about the connection between concentrations and rate. I want you to think about what's going to happen to the rate if H2 is doubled while the concentration of NO remains constant. So give that some thought and answer the question. Okay, so if you said the rate doubles, you'd be correct. Now we can just use some simple numbers to figure this out. So what I know is the rate is equal to K times the concentration of NO squared times H2 to the 1 power. So I know that rate is going to be, K is not going to change, so NO is going to remain constant. So let's call the concentration of NO1, and let's call the concentration of H2. Whoops. See, the concentration of H2 is also 1. That's raised to the 1 power. 1 squared times 1 is going to be 1. But if I hold NO constant like it says, this is still going to be 1. This is going to be now, I double this is going to be 2. So it's 1 squared times 2, and this value is going to be 2. So the rate is going to double. Okay. Now let's take a look at this one. Same equation, same rate law. What happens to the rate if, not in this case, NO is doubled while H2 remains constant? So give it some thought. Okay, so if you said the rate quadruples, you were correct. So if we again use just some simple numbers, and in the first case we say that this is NO squared and H2, and if we say the rate is doubled for NO, we're going to start with the value of 1 and we're going to change it to 2, right? Both of these will be squared, and the value of H2 remains constant in this case. If I multiply those out, here my value is 1, and here it's 2 squared, which is 4 times 1, or 4. So my rate quadrupled. Okay, we're going to stop right there.